Yeah, he's making great progress.
Do the trick. It's also good on meat, so what I need to do is to slice it up while it's soft.
Yeah.
Once it's gotten cold, it's
I don't like today, so
It's a brick.
this one. Oh, you want this one? Okay. If you want this one on, this one is working now. Yep. We don't have the one that usually gets to Zoom, so got it. Yeah. It should still be fine, but there might be a few minor audio. What's the? It's Newton North High School first robotics STEM festival. So it'll be middle school and other students presenting STEM optics, career paths, and standard optics.
We'll be presenting.
We'll be presenting. Yes, we would be having a table at one of these STEM festivals, like the events. So probably our standard demos. A couple new ones that I've worked on. So we are now live with the microphone. People on Zoom, all 6 of them can hear us.
No. I meant to turn. I thought I turned this off. Yeah. Okay.
Yuri has not been coming regularly for a good 6 months now.
Yeah.
So that puts that extra burden on us. I'm trying to figure out.
Oh, yeah. Right. Yeah. Well, you're right. Yes, he is.
Just your hard working yourself to do it.
Mm-hmm.
While everyone's putting their chairs together, thanks again for coming out. Want to have 2 announcements really quick. First, our next Optica speaker will be on Thursday, December 14th. It will be at Hamilton, Brooks, Smith, and Reynolds, so right around the corner from here. There is a new location, so please make sure to check if you're coming in person for their new location. And that will be, sorry. And the title of that talk will be System Aware PIC Design for LiDAR, Quantum, and Telecom Applications. Also wanted to announce on December 16th, on that Saturday, right after, we'll have an outreach event at Newton North High School. It'll be the first robotics STEM festival, where there'll be middle school and older students, and the NES-Optica organization will be presenting some optics demos and just kind of discussing some optics related career paths with the students. So if you're interested, please reach out and let us know, and we can get you involved. Second. All right. And last but not least, I want to introduce our speaker tonight, Tristan Swedish. So thanks, Tristan, for coming. So Tristan is the co-founder of CTO of Ubicept, which is a startup here in Boston that specializes in signal processing, single-photon counting sensors. For the past decade, Tristan has worked on real-time sensing problems in places such as Raytheon, Meta, and Skydio. Tristan has a bachelor's in electrical engineering and physics from Northeastern University, where we overlap for some time, and his PhD from the MIT Media Lab, working under Professor Ramesh Raskar. In his graduate work, he developed methods to solve optical inverse problems, such as turning objects into cameras and seeing around corners. Tristan's passion is to leverage the combination of optics and computation to improve the robustness of machine perception for better safety and autonomy for all. So without further ado, Tristan, take it away. Thanks for coming.
Awesome. Thanks, Will. Yeah, so today I wanted to talk a little bit about Ubicept. So this is a company that I co-founded with some professors at MIT and University of Wisconsin-Madison. And I'll talk more about that later in the talk. But the plan, I think, will be kind of taking a step back and trying to motivate why did we even start the company in the first place. So the beginning of the talk will be a little bit more high level, talking about what single photon counting is, kind of the trends, and then I'll get a little bit more into Ubicept. But the talk is still kind of from the perspective of Ubicept. So if there's any
Thank you so
questions,
much.
happy to try to answer them. And then towards the end, maybe we can get a little bit more into the weeds. There we go. Okay, so really what I'm going to start with is this promise of photon counting or quanta image sensors. And I'll talk about SPADs, but the really important part is the single photon part. And some recent advances, as well as Ubicept's vision. And so to motivate a lot of what we do at Ubicept is to look at and notice that visual perception is ubiquitous. So most industrial applications, especially ones that we'd like to maybe automate or make more safe, are in environments that are really challenging to see. Even though they're really challenging to see in those environments, like they're dusty, maybe dark, maybe there's really bright lights, often humans can still operate there. So the human eye is incredible. But if you look at the sort of parameters of how the eye perceives the world, we, on paper, have sensors today that are maybe better than our eye in some regimes. So why is it that human perception is still better than image-based perception? And I'll sort of zero in on image-based perception, and really frame-based perception is the key there. So that's on the industrial space. It would be great if we could have visual perception that could work everywhere. And why visual perception? When I say visual perception, I mean using the visual spectrum. That's both ambient light, things that are bouncing around, but also using visible light. And one of the motivations, you could say, is that nature has really zeroed in on visual perception. It's ubiquitous, and pretty much anything that moves in nature, if there's light, except for maybe cave spiders that still have visual eyes, but maybe don't use them, have eyes, and they use the visual spectrum. And there's a lot of reasons for that. I'm sure a lot of people here in the room can appreciate. You have the optical window, light moves through water, but there's also something about the ability to direct light. You have different materials that are low cost that allow you to form images. And so those combination of things mean that there's sort of, and I think this you can justify from a physics point of view as well, that optical imaging is something that is practical both in nature and also can be produced. You can create systems that are low cost and scalable in the real world. So what's the problem with visual perception today? I think if people have used the latest version of ChatGPT that now has image-based understanding, you can take an image, you can run it through their their visual transformer that then ask it questions about the image. It's incredibly good at understanding the world. It's actually really impressive. But despite these incredible advancements, you can't see information that isn't there. And we think that that's really the key missing piece. So when you look at fundamental image loss, that happens at the sensing level. It doesn't happen in any post-computation. You can't undo motion blur. You can't undo saturation due to dynamic range. And if you have too much noise, you can't overcome that amount of noise. And so that's represented in these images here. And these are really practical problems. If you're seeing something that's moving fast, you have motion blur. If you reduce your exposure time, you might have too much noise. And if you have high dynamic range, it's really difficult to use different computational methods to overcome high dynamic range, like bracketed exposure and so on, while things are moving quickly. There's another challenge, which is we often use multimodal methods. You might use LiDAR and cameras together. And if you're using this two different sensors, you necessarily have some parallax. And that's represented here. You have an image of a camera and a LiDAR. This is actually a LiDAR that's in the iPhone, which is, we'll get to in a second. This is kind of a little alluding to something later. But that creates parallax, and you have occlusion between those two. So they will see different perspectives, and because they are separated, the apertures of these two imaging systems are separated. You also have the problem of misalignment over time. So in a practical system, you might have some calibration that say, here's the direction of this LiDAR pointing in this direction, and here's where the camera is pointing. But over time, those two will drift apart. And how do you detect that? How do you keep that from happening? So that's really the motivation. That's the problem. And maybe we could ask ourselves, okay, here's how existing maybe CMOS or conventional image sensors work. And this is an analogy that we use that might be overly simplistic for some folks here, but we'll come back to it later because I think it's there, is that if we can think of pixels in an image sensor like buckets, and buckets accumulate water over time. These raindrops are photons and they fill up buckets. And then at some point, we measure how much water filled the bucket. And the volume of water tells you how bright each pixel was. And that information is then read out using an ADC. So you know, in an actual image sensor, you have a capacitor, you measure the voltage. And so that analog signal is converted into a digital signal. And that's a really tricky situation. So every single time you use an ADC to sample that, to make that measurement, you introduce a small amount of noise. And so you have a choice about how big these buckets need to be. If you have a big bucket, you can hold a lot of light, but at some point they'll saturate. You'll only be able to detect so much light. And when you have a really small volume of water, if your ADC has too much noise, you're not going to be able to detect that. You're not going to be able to see that there's only a few raindrops. So you're not going to be able to see both things that are dark and bright at the same time because of the size of these buckets. But also because you must expose over a length of time, you'll introduce motion blur. So these raindrops of a moving object in this cloud-shaped car will produce motion blur. So that's really describing how at the analog level, so at the point where photons are converted into electrons and stored in a capacitor, you're losing information. So that's really the problem with conventional imaging today. And so we say, well, what properties of an ideal, and I'll put ideal in quotes, you know, I think these are things that would be nice to have today for perception. And one of the things that I made an argument before earlier is that ambient light capture in the visible spectrum is important. So there's a couple of reasons for this. We want to be able to have systems that are going to work in the world. We built the world and our working environment around our visual systems. And so using optical imaging allows us to kind of understand the world that we've built. So this would be for things like cars, looking at road signs, as well as other robotics in the built environment. So having contrast in the visible spectrum is really important. We also, so in that case, we want to be able to apply color filter arrays in the visible spectrum. And this third point, I think, is a point that is really practical, is that we have an enormous amount of data that we've already collected in the form of images in the visible spectrum. And this data has been used to create computer vision models. They're sometimes called foundation models today for downstream computer vision that are incredibly good. And if we were to invent a new sensor or a new type of image modality, it would be difficult to overcome the advantage you get of having an existing large data set that's been produced by existing image sensors. So there's a big advantage of using ambient light capture today. There's another aspect of this, which is if you can synchronize with active light sources, you can make your imaging system a lot more powerful. So LiDAR or gated imaging has been used to be able to do ranging or remove things like scattering and fog. You could do photometric stereo or structured illumination. And those things are quite easy to do with optics. We already have those tools. We already have methods for doing that. And so this is really motivating. Well, we still want an imaging system in the visible spectrum that have these properties. And so this is a little like a table put together, just looking at conventional image sensors here at the top. And then this QIS or quanta image sensors. These are photon counting image sensors. So these are image sensors where the pixel is so small. These are sometimes called jots. And there was a company created called GigaJot that is able to detect single photons using a conventional CMOS image sensor by using very low noise ADCs and small pixels. They have high spatial resolution. The pixel pitch is quite small, but the temporal resolution is low because you still have to read out the data off of these pixels quite fast. And when you read out data quickly, that heats up the system and your noise goes up dramatically. They're not quite as good at low light for that reason, have limited dynamic range, and the ability to make them programmable, and I call this kind of exposure flexibility here, is limited. You still have this process where you're counting photons, but I think that the conventional image sensor is improved with quanta image sensors in many of these domains. And there's another technology which I'll get into called SPADs, which are single photon avalanche diodes. And SPADs have conventionally been used for medical imaging and LiDAR, and their spatial resolution isn't quite as good today. This is improving with 3D stacking. The pixel pitches of systems you can buy off the shelf are between 10 to 20 microns, but in research results that have been presented by large sensor manufacturers, there's high-resolution SPAD arrays that are currently at 3 microns. Temporal resolution is excellent. So one of the advantages of SPADs is that they have very high temporal resolution, and you don't have to enforce the idea of a frame. You don't have to read out frames. You can think of different ways that you actually can convert measurements into action. And I'll kind of really being high level here, but I'll get into what that means. They're pretty good at low light. SPADs today have limited fill factors, but those are improving. So with 3D stacking technologies, the fill factors of these pixels will get better over time. They have very high dynamic range. This is something that's a little counterintuitive, and I'll explain what that means. Like, what does dynamic range mean for SPADs in a bit? And probably the most interesting thing is that they're very flexible in terms of how you take data that's coming out of them and using them for computation. So I'll describe a little bit about what SPADs are. A lot of what I'll be discussing is that SPAD-like data is really what's important. So SPADs are single photon avalanche diodes. They are somewhat related to avalanche photodiodes. Avalanche photodiodes typically run in what's called the linear mode, where you have this reverse bias PN junction, and when a photon hits it, it creates a measurable signal that then creates this avalanche process that can be measured as a photon hits the APD. In a SPAD, you put the breakdown voltage very, very close to sort of like an unstable situation. So a single photon can induce an avalanche. That creates this runaway current, and that runaway current is very easy to detect. And then what a SPAD does is it quenches that runaway current very fast. It tries to recoup as much energy as possible by capturing the electrons that are being pushed through this current. And then this system is recharged. And so what that means is that you're able to detect a single photon, and you get a very precise timing of when that photon hit the SPAD. Yeah.
How long does the current avalanche drive? Was it quenching and recharging?
So it really depends on the exact design, and so there's some SPADs that have been optimized for very, very short recharge times. And I'm not going to remember off the top of my head, but nanoseconds, it's kind of on the order of nanoseconds for recharge time. When the SPAD is avalanche is induced, there's also some uncertainty of exactly when that timing occurred, and this can be called SPAD jitter. And if you make many measurements, the accuracy of detecting when the avalanche occurred can be very, very precise, sub picosecond. But the recharge time itself takes on the order of a few nanoseconds. And don't quote me on that exactly. It turns out that that's the quenching circuit is very fast, but I want to be super clear. I'm not a SPAD expert. What we do actually is using the output from these SPADs. So really what's important to us is how quickly can we take a photon detection and it's ready to detect another one. Yep. That's right. Yeah. So so here's a good diagram on the right here. Maybe I should pointer. Let's get the. There we go. Okay. So this is a diagram of a conventional SPAD array today. So if you can produce these SPAD arrays today, they have these are individual SPAD pixels, and then the pixel pitch today of a typical SPAD sensor like this might be 20 microns or so. And inside each pixel, you have the area that can detect photons. This is the SPAD itself, and the fill factor is quite small. So you have a kind of a small region in which the photon can be detected. Then you have the digital front end. This is some electronics and some digital circuitry that detects the avalanche and actually does all the quenching itself. And then you have things like counting logic or time conversion logic. So this is now in doing just regular digital computation. You know, you can put arbitrary computation here because these pixels are produced with a CMOS process. This architecture is changing a lot. In the last few years, this is moved to a 3D stacking architecture. So the detectable area or the photosensitive area of the pixel is growing. The fill factor is getting much larger. And the flexibility of what kind of digital logic that you can put associated with each SPAD pixel is also increasing. So this is showing what maybe a SPAD pixel has looked like conventionally, but a lot of this is becoming less relevant. But this is a good view of kind of the pieces that you'd see in a conventional SPAD system. So the SPAD itself is just this photo area, have some electronics that will do the quenching, the avalanche and recharge, and then the digital front end and counting logic is really very dependent on your application. So, sure.
For the SPAD, is there like a band gap, or how is the SPAD like to be responsive?
Yeah, so most SPADs, so the vast majority of SPADs are created in silicon. There are like in-gas SPADs that people have demonstrated, but silicon still has a band gap, which is going to induce the avalanche. So you can think of like these SPAD pixels. Again, this is not, I'm not an expert here, but the photon, when it's hits the PN junction, there's actually an impact ionization process that induces this avalanche for SPADs. And the reason for that, that impact ionization can actually do that, is because this reverse bias of the diode is pushed quite far into this region. And so when the diode is put in this reverse bias, and then a photon hits it, the impact ionization pushes it into this regime where now you have this huge current spike. That is due to the band gap of silicon, which makes it sensitive in the visible. And that would be kind of my limited understanding there. I'm sure SPAD experts could educate me more on that, but that's how I would describe it at a high level. So now this is the point in the talk where, you know, we have this technology, we have SPADs, but individual photons can induce a signal that can be measured, and that signal has high temporal resolution. So this is where we move into what do we do with the signal? And I think what's quite interesting about these sensors is that you move from an analog process to a digital process as soon as you detect that current spike. And this is why, you know, the details of the SPAD and why they work, they're super important. But a large amount of our focus is on the digital part. And what's great about the digital part of this is as SPADs improve, as these metrics get better, everything I'm about to share will still be true. And what I'm sharing here are a way to think about how can you use these SPADs to form images, and how are they used in practice. So I guess the first point is what is photon flux? So the amount of photons that are hitting your pixel at some period of time. And there is, I guess the first thing is there is no such thing as a real photon flux. There's no continuous level, a light level. You have individual photons. So
some
if
shoppers
you were
use
to make a
two
measurement in a
kinds-
really
two
short
kinds
period of
grid
time,
rolls.
there is no image.
Those five
So in order to
Now,
estimate that photon flux,
two
you
different
need to have
styles. One has a
some
lot of
measurement
cream
over
on it,
time.
the other doesn't.
And so there's two
And
ways to do
so
that.
he didn't have
The first way is
seven
that when a
of the
photon
one I designated.
introduces an avalanche,
So he
and then
picked
there's
up
some
two
recharge or
of the
dead
other
time,
type, which I dearly love.
the avalanche is
You know, I could
detected,
eat either one
and
of them.
the SPAD is actually
But,
not
you
sensitive
know,
during that time. So
the
this is
shopper
this
would say,
timeline.
"Tuck out."
We're not able to detect
But he
any
said, "What about
photons,
these two?"
and now it's sensitive again.
That's it.
Once a photon arrives and induces an
I didn't
avalanche,
really care which style.
now we make a detection, and any
They're
following
cinnamon
photons
buns, and they're
we're
big
not going to
ones.
see.
Did it. So
That before we have
was the
the
only thing he
SPADs
ran
recharged
into.
and ready to detect photons again. So what we could do is we could count photons. So we could just say, I'm going to count every single time I see a photon, and over some period of time, I'll put these in an accumulator, and I'll measure the amount of light. The other way that you could do this, which is quite interesting, is you can estimate the interphoton timing. So rather than counting photons, you can put a timestamp on each avalanche, and you can measure how far apart these photons arrived. And so with each interphoton timing signal that you make, you can estimate how bright the scene is because, well, photons are arriving due to a Poisson process. There's an exponential distribution of when they arrive. So once the probability of detecting a photon drops exponentially, and that's related to the decay of how bright, or the decay of that exponential distribution is related to how bright the scene is. So photons are distributed kind of randomly in this Poisson process, but you can estimate how bright a scene is by looking how far apart these photons are. And so you have to make a number of measurements in order for that variance to reduce, so you have a good estimate. But it's a really weird way to think about measuring how bright the scene is because we're no longer counting the number of photons. Yep.
Oh, okay.
Right. So for SPADs, that's not the case. It would be that once the avalanche is triggered, it happens, and that amount of energy. It's not possible.
Good. Yeah.
Yeah. So, and I think, okay, so this is, I think, an important point is this dead time may seem like a problem. Okay, so we can't see photons for a period of time after the SPAD is triggered, but it actually creates a non-linearity that introduces soft saturation. So you don't actually have to count every photon. And we'll talk about that in a little bit. And probably the most interesting thing about SPADs from a computational perspective is that there's zero read noise. So I can sample that SPAD signal as many times as I want. And I have a high, I don't pay a penalty. So I don't have an ADC that I'm sampling the voltage across a capacitor. When that avalanche is triggered, I say I think that there's a photon. And in practice, you still have thermal effects. So avalanches can be induced by thermal effects. But that noise due to thermal effects has dropped dramatically, so that it's not a major problem in modern SPAD pixels, especially as the pixel pixels have reduced.
I can even water because I can see the roots.
So adding a little bit more detail here for the counting of photons. Photon counting is still the predominant way that images are produced today, so I'll focus on that. When you have an avalanche, you detect a photon, and we can then update a counter or like a single bit on the pixel to make a 1 or a 0, and over time we can then put this into an accumulator. And so for these four samples, we've counted 3 photons out of these 4 buckets.
Go over here and see. It's got an ETA yet. No ETA.
It turns out that because of this dead time, you can model the probability of a flux given these counts. And then this is just 4 counts. This is not a large number. So if you look at the total number of binary frames or the total number of binary measurements, this gives you a soft threshold of the number of photons that you can detect over a given period of time. And in this case, we have 3 out of 4. And that will put you on a curve here. So as you get closer to saturation, you'll slowly approach the number of frames that you can fill for that period of time. And this curve, I'm not going to show, happy to talk about this offline. but
Sure
this
it does. Yeah, I've got it
curve is due
plugged
to this
in.
dead time.
Charging.
So
It's setting up
if you
already.
model the probability of
So-
detecting a photon over some period of time, that
Okay.
probability is related to how bright the scene
Yeah,
is.
the one, two, three.
And when you have dead time, this
Yeah.
becomes a Bernoulli distribution of I
It's
detect a
in-
photon or not.
here's
So
us in the-
what is the probability I detect a
Okay.
photon within some period of time? Some, in this
So
case,
let me try again and
this
see if I can-
time between I'm making measurements. And if I detect a photon, then I increment this counter. But if I have more than one photon detections, then I still have just one single detection. But by looking at
Oh,
these 4 measurements,
yes.
I can still estimate how bright the scene is, even if I have missed photon detections. So it's really about
GPS, yeah.
hopefully, that's
I
kind
can
of gives the
tell when the
intuitive
sound
understanding.
stops, it'll be,
And just as a comparison, this would be the number of incoming photons that are incident on the SPAD. And the average number of detected photons follows the soft saturation signal. In a conventional CMOS pixel,
Let's see.
the number of detected photons increases linearly with the number of photons. And once you hit full well capacity, you don't have, you've hit saturation. And so now you're losing information. Now, of course, in
Sometimes just
practice,
post an
it
ETA.
depends on how many photons you're counting. So if you
Let's
count
see.
more photons, you're going to have a
Here we
much better
go.
estimate of what your brightness is. If you only count photons, you do have an effective saturation because there's a very high probability that you will still be saturated
So it's just,
if you make many measurements of these 4 photons.
oh, wait a minute.
I saw
Here
that a
comes
hand
the
was raised in
map,
the
but I
Zoom,
don't
but I'm
have
not
an
sure
ETA yet.
how it's. I'll just keep. Maybe we'll for the folks on Zoom, we'll do the Q&A at the end. Or
No, not this time.
Thank God. Well, why am I taking him out?
all right, cool.
Tristan, can you hear us?
I know, I looked at him and decided.
So I think
yes,
this is
you're
kind of
right, we don't need
a super
more.
high level view of how SPADs have these soft saturations. Yep. Oh, okay, yeah. So in this case, this is just an arbitrary time frame. In practical systems, this is like microseconds between measurements.
Yeah,
Some SPAD arrays, and just for practical reasons, you have
Oh,
this.
good.
I should go back to the diagram here. So for
That's
practical
great.
reasons, each of these pixels has a SPAD, and then you have this counting logic, which could be the bit counter, and then you need to read off that data at some point. And so you're really limited by how often you can read that
I
data
didn't
off of
think,
the
I didn't
pixel.
think you would. I
And in
looked
that
at it.
case, if you have very low bit depths and a resolution that's in the, you might be able to call an image, a few hundred pixels by a few hundred pixels,
And
or
I
maybe
didn't see any
a few
bugs.
megapixels.
Thank you,
You're
Brian.
limited
Yeah.
by, it's about
Yeah.
a couple tens of
Hey,
bytes per
how you
second. But in practice, you're really limited in terms of frame rate,
Yeah, it's slow
or
picking
how
up.
often you
Sorry
can make
about
those
that.
measurements by the recharge time, which is
There
now
we
more in
go.
the, as I was saying before, like the nanosecond regime.
that. Just
So
call to find out
if
you're in
you
fair
didn't have
seas.
the practical limitation of bandwidth, SPADs could, you could consider SPADs as being
I
like
just called to find
able to
out if
make,
you were in fair
uh,
seas.
do millions of frames per
Good
second.
following
And
weather.
turns out there's a paper this year at a computer vision conference that demonstrated just that, which I'll show in a second. Awesome. So here's some SPAD development trends. So SPADs have been around for a long time. Actually, I think the original research papers are in the 80s and 90s, but SPAD arrays were introduced in the early 2000s, and they've been following exponential growth like most CMOS process technologies over time. And as they are using newer technology or newer process technologies, the pixel pitches are dropping, and the number of photons is also increasing. So I've taken this slide from a presentation at an image sensor workshop from Canon. And Canon, we'll talk about in a second in the next slide, has recently released a SPAD camera, in the 3.2 megapixel SPAD camera. So when I put this industry entrance here, this graph actually needs to be updated because there's now megapixel color SPAD arrays that are commercially available that you can buy. And we're also seeing research that's using 3D stacking, and we're seeing that this trend is following. So this is where we are today, kind of right on track. And what's, I think, quite interesting about this is we're now in this regime of a few megapixels where these sensors can be thought of as image sensors that would be useful for computer vision. You can see the world, and that's really what I think I'll mostly focus on when you talk about Ubicept. Great. So this is the Canon camera. So this is the 3.2 megapixel color SPAD sensor. This has a Canon SPAD sensor inside, and it looks like a conventional broadcast camera. So you can mount Canon lenses on the front, and it outputs images just like you'd expect from a camera. What the Canon system does is it outputs counts directly after integrating for a period of time, and those counts are used to create an image. So there's not a lot of computation, at least as far as I'm aware. I don't know how it works internally, but for how these images are produced, they still have artifacts like motion blur and potentially limited dynamic range and so on. And I'll describe in a bit how that might be able to be overcome by not thinking of SPADs as just conventional pixels that accumulate light in a digital counter, and thinking of the digital counter like a digital version of the capacitor used in conventional images, but instead thinking of SPAD pixels as a way to sample light and being able to change how you sample that to overcome these limitations. So Sony Semiconductor released a research paper this year with a 3-micron pixel pitch SPAD. And 3 microns is in the realm of security cameras, maybe a practical webcam. 3 microns is in that range. And this particular array has readout electronics and other electronics in a 3D stacking architecture, and it uses a copper-copper connection so that you can use potentially a different process. So you can have one process for the SPAD, and then you can use a higher resolution or a more advanced process, smaller gates for the digital computation underneath. So what we're seeing is in a move in industry that SPAD arrays are starting to become potentially practical, and especially high resolution SPAD arrays. So I think something else I should mention is that the array size of these pixels is this is about 640 by 1056. If you can't see that, so we're in the megapixel region on this research, and this is 3.2 megapixels. Now, if we look at the academic side, like what's happening with SPADs for imaging, this was ICCV is a major computer vision conference this year. The best paper award was a SPAD paper. So this is work out of University of Toronto, and this is a video that's showing this over time. And on the right, you can see that they reconstruct frame rates by using SPADs in a really clever way of modulating how they're making the measurements coming out of these SPADs and the time-stamped photons as they are time-stamped as they come out. And they're showing an image reconstruction. I got a Zoom notification. I'm just gonna.
Sorry, unmuted on Zoom, but I need to mute. Sorry.
Sorry.
Well, I kind of picked up an interesting gig that if all goes well, and it looks like all is going well.
And so this video on the right is showing a reconstructed frame rate from, I think it's at video rates, so like 300 hertz to 250 gigahertz, which is incredible. Huge range of temporal resolution. And you can actually see a light, a laser pulse moving through the scene at the end. Yep. That's right. So it's essentially like a laser, an unfocused laser, just like illuminating the scene. You can see that pulse laser move through the scene like a flashlight arc. There's some other work in academia. So this is some work that I did with Mohit Gupta, who's one of our co-founders, but is a professor at University of Wisconsin-Madison. And the idea was that you can use a spat array to capture all these photon counts. You can create a photon cube. And then by applying different processing, you can emulate other types of cameras. You can emulate event cameras, high-speed cameras, and you can even do things like dolly or trucking operations where you can track things as they move digitally. And the idea here in this work is that you can do maybe post-capture choice. You can capture your raw data, and then you can post-capture to create different types of cameras. So this is kind of just these super interesting world that's opening up. But there's some practical limitations. Like, what about memory and bandwidth? How do we store this photon cube? How do we create a commercially practical perception system that we could actually put out into the world? And I think I'm going way over our time here, but now this brings us to Ubicept. The idea with Ubicept is, can we do general purpose perception, image processing for photon counting sensors, and that would enable us to do ubiquitous perception. And we founded in 2021. So this is myself, my advisor, Ramesh Rasker. We're at the MIT Media Lab. And Andreas and Sebastian is our CEO. And Andreas and Mohit are at the University of Wisconsin-Madison. And Ramesh and Andreas worked together in 2012, and they showed this laser pulse smoothing for a Coke bottle. So this was kind of the initial idea of, what if you could capture light in flight? What could you do with it? And that turned into work to use these measurements, these light in flight measurements, to see around corners. So essentially turning a LiDAR into a kind of virtual camera that you can create on the wall. I'd love to talk about that maybe offline later. Andreas went to University of Wisconsin-Madison, continued this work with Mohit, and then Andreas's postdoc Sebastian joined, and they demonstrated seeing in corners in real time in 2021. And Mohit began working with SPADs to do general purpose imaging and showed how you could eliminate motion blur using this raw SPAD data. So we came together. I was finishing my PhD. Sebastian was coming to the end of his postdoc, and we were asked each other, like, despite these incredible AI advancements, machines can't see everything they should be able to see. You have things like motion blur, you have things like dynamic range. We have some ideas around how you could do light in flight. We have some ideas of how you could remove motion blur. Well, can we enable machines that can see at the limit of physics? And really the limit of physics is being able to count individual photons. And so our idea is, we could see everything if we can count photons, and that would allow us to have the best computer vision allowed by physics. So if you can see everything, then you have all the information that you need. Now, all we have to do is overcome those limitations of memory and bandwidth and all those things. But in principle, that's what we need to do. So in practice, we're not counting every single photon, but by thinking in this way, it allows us to come up with a different way that we might be able to think about the perception problem. Rather than forming a frame and training a computer vision algorithm to understand that frame, can we sample the scene in a way that's optimal so that then we can feed that into downstream processing and produce maybe a frame for a pre-trained model that was trained on image frames, but produce a frame that doesn't have any of the artifacts that make them not work as well. So really, the idea is, what if we knew precisely when each drop landed instead of filling those buckets up with water and measuring the total amount of light? So these have zero read noise, so we can look at these photon cubes, like a stack of frames. And when you have a conventional camera system, you accumulate these frames and you have blurry frames. Maybe you reduce the exposure time, and now you have noisy frames. And at Ubicept, we look at all of the frames. We look at a huge chunk of frames over time, and we can reconstruct an image that is low noise and also high speed. So you can do things like run a tracker on a corner detector, and you can track the suspension of this little toy car as it bounces along the surface. Yeah.
So if you bias your avalanche voltage, your breakdown, you should be able to adjust the dynamic range of your detection system to get different energy photons. Is that what you're also doing?
So that's a really good point. So that bias voltage will increase or decrease the probability of detecting a photon. It also increases the probability of noise and inducing an avalanche. I'll comment on exactly what we do, but like the point is that there are ways that SPADs can be modulated, and that's really powerful. You know, that you can modulate SPADs really quickly, and you can change those parameters. So yeah, that's true. You can change the breakage photon, and you change the probability of detecting a photon.
And that's part of the cube that photon cube is three.
Exactly. So this photon cube is a set of measurements that represent the samples that we're pulling from the SPAD.
Okay.
Yep. And so where do we lie? We're kind of this weird space where I did my undergrad in physics, but in grad school I really focused on computer vision and computation, and really focusing on inverse problems. So a lot of math. And what we think is that SPAD sensors give us excellent input to be able to apply some of these techniques to use for image formation. So at Ubicept, we're focusing on processing the raw data coming off of SPAD sensors and looking at applications that are uncontrolled environments like aerospace or mobility and industrial automation. And I'm going to show some demos now, and then I'll talk a little bit more about what we do. And one of the things that I won't show today, but I want to mention is that we can emulate event cameras. So if you're familiar with event cameras, the idea is that you only transmit pixels that change a certain amount. And conventional event cameras are produced using analog circuitry. It's like a photodiode with a comparator that when it changes by a certain amount, then it updates and it resets the capacitor. But we can do that digitally. And so that's what it was shown here. We also have ways of having a very high dynamic range. You benefit from SPADs having a soft saturation, and there's also other ways that you can modulate the SPADs we alluded to before. So this is what it looks like. We have a system that's set up in the lab. This is our SPAD camera that we have from our imaging partner. And we set up this system where we have a light level meter, and we have a pottery wheel that you can spin with this kind of toy scene. And the reason we did that is that we could run an object detector. So this is a pre-trained object detector running on both systems. And on the left is our solution running in real time. So we're capturing data from the SPAD, we're processing, creating frames, and feeding that into the computer vision system in real time. And then we have a low light camera next to it. So this low light camera was tuned so that we had a low enough noise that we could make detections when the system was static, but when the system's moving, that's when you have a lot of challenges. So
a message from Zoom.
Sure.
Compared with traditional CMOS sensor, this SPAD camera typically has lower saturation threshold.
So I guess it doesn't really have a saturation threshold. Like a SPAD pixel, when an avalanche is induced, you get a detection. There isn't really a notion of saturation in that sense. I think if you were to have an equivalent to saturation, it would be that you're making a detection every single time you recharge. So you have no information that you're always seeing light. But as we discussed before, you can change the probability of making those detections. And so we also have high dynamic range, and this is running in real time without motion artifacts. So typically, if you use like bracketed exposure techniques, you'll end up with motion artifacts. These techniques are embedded today in modern image sensors. Like the digital logic of doing these bracketed exposure is actually on the image sensor itself. But you still can't get around the problem that each exposure is going to be different in time. So even if you modulate the exposures and combine them, they're captured at different points in time, and that's going to give you motion artifacts. So this is showing a light, this iPhone camera. You can see the LED and the scene all reconstructed in real time there. Here's a use case. In this use case, we're looking at low light, high speed imaging. So high speed imaging, you typically need a lot of light, and reason you need a lot of light is to overcome the added noise from reading out a high volume of data. So when you read out a lot of data, high speed cameras are pulling data off of the image sensor, heating up everything, and it's a challenge. You need lots of light to overcome that noise introduced. With SPADs, we can do high speed imaging with much less light. And actually, in this comparison, we're showing a conventional camera where you're strobing the light. And this is a small piece of a wristwatch. So if you use continuous bright light, it would heat up the metal elements and you wouldn't get a good measurement. And on the right, we have making our measurement with the SPAD, and you can see the wiggle of the spring. So that's showing a high-speed reconstruction from our SPAD data. Yeah, that's right. So this spring is actually the coil of the spring is wiggling.
On some of the other example data, you have like an equivalent frame rate.
Mhm.
What do you have an estimate of what the frame rate?
So if I recall, this one is like on the order of like 3,000 frames per second. Yep. And practically, our system can be much higher with less SNR.
What is the practical upper limit to the speed, and how is that impacted by the necessity to collect that full data queue?
Yeah, so the practical limit is not so much the limit due to SPADs is the recharge time. So that's tens of megahertz. That would be the practical limit. But because you need to do some computation and you need to push those bits around, you're limited by how much memory you have on each pixel or your bandwidth of pulling that data off. And so that bandwidth isn't changing. We're not like using more bandwidth than you would with a conventional camera. And we're not using high speed connections to push this data in. We're encoding that data more efficiently and then pushing it over the same sort of bandwidth limits that you have. So in practice, you're limited by those things. And so it would be application dependent. So in this case, our practical reconstruction is on like 10,000 frames per second. We think that can be improved quite a lot as you move computation closer to the pixel. Here's another example of license plate detection. This is a kind of a problem you could generalize to any computer vision task where you have both dynamic range and low light. This is a license plate detection. Typically, license plate readers have lights on the camera because license plates are retroreflective. But in this case, we just point our camera out the window. I'm going to see if I can get it to play the video. In this case, the video is not playing. And these videos are on our website. But here's another example that's pretty similar. You have, in this case, we have a automotive camera that's pointing out the side of a car. And when you use the camera to look out the side of the car, you have motion blur at night. So this was captured at CES in Las Vegas this past almost a year ago. And you can see motion blur. You have this high dynamic range scene. And this was captured with an automotive camera that's graded as high dynamic range. And then this is our reconstruction on the right. This is showing a reconstruction and also our high dynamic range. So you might see some artifacts around the people. That's because we used a really simple method for viewing the high dynamic range data, because these lights and the fountains from the Bellagio are super bright compared to the people. So that's from the HDR. You can even see someone taking a selfie with a light ring, and this person as we pass them. Yeah.
What's the salt pepper noise you see?
Yeah. Okay. So this is a great question. So some people, I think when they first see this, is like, oh, you can see the stars. Well, actually, that's just our fixed pattern noise. So we have since fixed that in our system, but you can see in the dark regions that you still have manufacturing defects in the sensors, just like you have in any image sensor. And so you can think of these as like stuck pixels, dark pixels. Yep.
When can you see the stars?
In this case, I think is a good question. I think the atmosphere, like the sky itself, is so bright due to the illumination of Las Vegas that you're getting backscatter from the sky. So I'd be curious in that point if we actually could see the stars with our eyes, but I probably not. Awesome. So here's another example with a conventional camera, and we're doing QR code detection in low light. And this is playing each frame of a rolling shutter camera that would be typically used for this application. And this is a package being thrown back and forth, kind of like thrown and rotated. And here's a reconstruction we did of that system. We kind of slow it down to that that 10,000 frames per second, and then speed it up again. So there's a lot of other demos on our website, so ubicept.com. I'd be happy to kind of walk through that maybe offline. And we have eval kits available. We're mostly doing leasing or projects together. So if you have an application you're thinking about, we're looking for partners to do joint development, because we have a technology, we have our software, we have some hardware, but what we're looking for are applications where we can take this to scale. So we'd love to chat with you.
Eventually advancements in resolution and fixed edge, like
Yep.
where are you working at, like with your evaluation?
Yeah, so our evaluation kit today is VGA, native VGA. I don't know if I'm not gonna share that, but it's right now C-mount lenses are sufficient. So the C-mount lens will give you like an image that you'd expect from that. It's not hundreds of microns. It's also not 1 micron, somewhere between. And it's a good question. So the VGA resolution, we can also upsample. So we can produce a higher resolution image because we're sampling so fast. When you have moving objects, if you're okay with using some super resolution or upsampling methods, then you can actually end up with a much higher resolution. But our base method for reconstruction doesn't introduce any inference, and that method requires some inference. So there's kind of like one more thing, and I know I'm coming up a long time. We're okay. Oh, we're good. Okay. Is I talked about how at the very beginning we were inspired by this idea of light in flight. So being able to see things that are moving very fast. That led to work to see around corners. And most of what we've done and shared publicly at Ubicept is passive imaging. So not using any active illumination. Our system is just using ambient light. We process these photon cubes to produce high quality images that you can use downstream task, and we can process them in real time. But what happens when you start adding an active illumination source? And this, being a company that was founded by people who are really passionate about seeing around corners, we're at the point now where we can start applying this application commercially. So I'll give a really high level idea of this. And I think after the talk, if we want to talk kind of where we are, the idea is that we can create a projectable motion detector. And so what is seeing around corners really? It's being able to project a pattern of light that's visible to you, and then using multiple reflections, so multipath reflections from this projected light, we can then detect moving objects around the corner. So this is a visualization of kind of being able to see through this bus. Oh, there's a car approaching. We can avoid running into it. This is a video. It's a little scary. Everyone's okay. But you'll see in a moment what I mean as a potential application here. And so, yeah, we're super lucky that this driver was able to see that and slam on the brakes. And so looking at our system, how can we design a system that could avoid this? So with a non-line of sight system, Andreas and Sebastian demonstrated a real-time non-line of sight setup. In this case, we have a SPAD camera, and they had a SPAD camera and a laser source. So this is a femtosecond laser source that's sending a pulse of light into the scene on this surface here. And the SPAD camera is focused on this wall, and the laser source is projecting a pattern of dots onto the wall surface. And using this data in real time, you can reconstruct an image of this 4. And you can see the reconstruction on the laptop screen on the right, just kind of prove that this is real time. This is quite strange. It turns out the reconstruction algorithm for this is effectively turning this wall into the aperture of a camera. So mathematically, we create a camera that has millimeter resolution, sort of like millimeter wave camera, where the aperture is the size of this wall. And so kind of give an idea of how that works. You send a pulse that scatters everywhere. It hits the hidden object and comes back to the camera on the third bounce. So here's the first bounce, second bounce, and the third bounce. Yeah.
In the same concept can be used for looking through scattering, or with a limitation of how many scattering effects you have.
Yeah, I mean, in principle, you can do that. What this method does in order to do this reconstruction really fast is we are assuming one scattering event, and that's useful in this case because we're turning this wall into an aperture of a camera. So to do like volumetric scattering is a different problem. It is much more difficult. In this case, we have a single scattering event, and the optics of the setup and the particular reconstruction method we're using makes this work at real time. So I think there's a lot of kind of components of this that seems magical. Being able to see through volumetric scattering is still a very hard problem. But this method is not directly applicable to that.
Structured like something modified that time of flight that is between scattering events.
I'm not sure. I think I'd love to chat offline, like what you're thinking, because yeah, I mean, it'd be sounds interesting. Here's a reconstruction, some more results of seeing around corners of a person moving in the hidden scene, and you can see the reconstruction on the computer and also in the top right. And to connect this to the system we had before, you have your imaging system could maybe have been on this truck. You have your hidden object, you have your occluder, and then you have your relay surface, or the surface that you're bouncing light off of. This is just kind of visualize how you could use this system. And not getting into tons of details for this setup, but the relay surface, in this case, the relay surface where this blue square is, you could ask, okay, well, does it matter what the distance is between this blue square and your detector? And interestingly, because of using this relay surface, the amount of light that you capture within a certain region that the SPAD pixel can see, so sort of the area of the wall that the SPAD pixel is imaging, grows as you get further away. So as long as the surface is still within the field of view, your signal is largely maintained. So it's kind of like analogous to, why does a wall not look half as, it does not drop off as you get further away. You're actually capturing more of the wall and more light's coming at you. So in a system like this, the distance between the green square and the blue square can actually be quite large. Andreas did some work validating how this might be able to use it extremely long work or really long ranges. And there's been papers produced by other groups, academic groups, that have demonstrated non-line of sight signals over 1 kilometer away. You're going to lose resolution. That's right. So you lose resolution. Now, you do lose resolution in one way, in some sense, but the resolution of the reconstructed of the hidden scene is related to the size of the aperture of the relay surface. So if your relay surface is really big and you got farther away, as long as you could still see the relay surface, because the aperture is larger, your resolution actually doesn't decrease. Of course, there's like practical limitations, but that's the idea. And mathematically, this relay surface, I kind of mentioned it sort of becomes like the aperture of a camera. That's really how that system works. So and I'll give the super high level idea just because I think it's really cool, is each signal or each measurement we make between the laser source and the detector you get when you see photons, the backscattered photons, and you timestamp them and you create a histogram. So you have a histogram in time of how many photons you see. That histogram is like an impulse response. So you have the impulse response kind of the scene. And with an impulse response, you can now send a virtual signal. You can emulate what a virtual signal would look like. And so if you sample this surface in a grid, you can create a virtual wave with a wavelength that has, say millimeter wavelength, and you can create an aperture of this relay surface that has a resolution of a few millimeters. So it's kind of like a projectable millimeter wave imaging system, sort of like a synthetic aperture or something like that. But that synthetic aperture can be projected. You don't have to put the emitter and detector somewhere, because that emitter and detector are on a scattering surface. So that's kind of, yeah.
How do you not lose directionality of the scattering, the targeted interest, right? Wouldn't a guy 3 paces to the left or 3 paces to the right, but at the same distance, produce the exact same pattern? So
you end up so the reconstruction itself creates it's a volumetric reconstruction. And I don't think I can so there's not any ambiguity about where the location of the object is. The challenges are really about making sure you can get light that is scattering onto the object itself. So there is a region in which the object can be detected, because you still need light to hit it.
But so you're scattering off that wall, and then it's not just a kind of light back off the wall, or is it
right? Okay, so I will I have some slides kind of to visualize how the reconstruction works conceptually. But what I'll describe here first is you have a light source on the wall, and then you also have a detector somewhere else on the wall. And that pair is what gives you that time profile. And in this case, the camera has multiple pixels. So there's multiple camera pixels on this wall. And there's also multiple, each time you move the laser, you have a new set of measurements. So this is actually making, sort of you think of this as a measurement for every position of the laser and every detector. And that gives you a lot of, a lot of pairs of these detectors. And so it's kind of getting to how does this work? So almost done. I just want to kind of give a little bit, leave with a little diagrams and math here. Recall that in an ellipse, you have these D1 and D2 is constant. So you can draw an ellipse by having 2 points, tying a string between them, and having your pen kind of taut and moving it around, and that will create an ellipse. And so in this case, we have our laser and our detector that are looking at 2 different positions on the wall, and we can measure the time delay between when the light was scattered off of the surface and when it returned. And that time delay that we measure is D1 plus D2. And that means that the hidden object is on this ellipsoid or spheroid surface. And so you can imagine how this could be generalized into 3D, but in 2D, it's I think pretty clear. And so when you send the laser pulse, you get a smaller amount of received light, and that gives you your time delay. And what that means is that you can isolate your object to this surface of this ellipsoid. If you add another detector, so this is having multiple detectors, now you start to be able to look at how you can localize the object. And of course, in practice, the resolution will decrease with distance, or when you make a measurement, you have some uncertainty, and that determines your resolution. Yep.
Go back to Josh's question. All these conic structures have symmetries to them, and so consequently, if an object is at the same symmetrical point on your conic, you could have ambiguity as to where it might be in your wall.
Right. So yeah. So of course, when you're just thinking about intersecting these surfaces, you end up with problems like this. Today, this is the explanation of kind of where is the signal coming from, but the reconstruction methods today are moved way beyond these models, and those methods are not don't have those same limitations. There is a lot of interesting work in the literature about different trade-offs, but in this case, because we have this image surface, it kind of limits where those intersections can be. That really simplifies things.
In this case, each pixel is a detector.
Yep.
Working with thousands.
That's exactly right. So that's why we like to call this like a projectable motion detector, because you're projecting the detector onto another surface, as well as projecting the emitter, because you can have a focused laser point on the relay surface. That laser point becomes a source that illuminates everything in the scene. So you could emulate this by putting like a single pixel detector and like an LED or something on this. That would be giving you that. Yep.
Practicality, like, you need it in a dark room. We're doing this outside, and there's lots of natural light.
Yeah.
A second.
Yeah. So I guess two things. So one is there's a lot of work in the literature on this in particular. You can use methods that are used in LiDAR, so for seeing in bright light. You can use time gating, things like that. Also, bandpass filters in wavelengths you don't have as much ambient light. So there's a lot of solutions to that problem. And actually, that work showed how this reconstruction is robust even to lots of noise. That was probably the big contribution of the reconstruction method. Is it's very, very robust to noise. And I didn't show the video. We should show this. Is that you can turn the lights on and off, and it doesn't change the reconstruction. It just increases the noise a little bit, background noise. Yep.
System-wise, how big is that? How big is your system in portable?
Yeah. So the system can definitely be made portable.
How small?
It really depends on the system parameters. If you want to see something, if you want to be able to do a reconstruction, like we showed in the video, this system, the SPAD camera it's roughly the size of a webcam. I would say it's harder to see in this image. And then the largest piece of component of this system is the laser, because this is using a femtosecond laser. There's LiDARs, for example, don't use femtosecond lasers. They're more nanosecond. Those lasers you can use like VCSEL arrays that are very compact. And you can also use these, and the SPAD detector itself is very compact. So that reduces your resolution, but you effectively can create a system that's very small. That's right.
Okay. Thank you.
Awesome. So yeah, I'm just going to end with some closing thoughts. And this is like the main idea I think that we have is that counting photons allows us to integrate light digitally. So this allows programmable logic to replace fixed analog methods. So instead of using analog methods to integrate photons at the pixel, if you can digitize photons directly, you can start using digital methods. This will enable rapid design of imaging systems without changing the hardware. So using the same SPAD array and logic that could be programmed, perhaps. You upload some firmware on logic that's running a little tiny computer that's on the SPAD array. And this is not our idea. This has been proposed for quite a long time. That with a single system, you can now emulate many different types of imaging systems. And I think another kind of interesting idea to tie this non-line of sight stuff back to passive imaging is, could we move towards a single aperture for optical perception? So rather than, and in-depth information is incredibly important for perception today, could we have a single camera that could do both depth and passive imaging? And that single aperture means you eliminate this parallax problem and calibration problem, but it also simplifies the system, makes it smaller, more practical for use. So this is kind of a food for thought that I wanted to leave with. Thanks.
Thanks.
Questions. Tristan just requested that we turn off the recording for this section just so he can be a little more candid with his responses. So let me just do that really quick.